Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video demonstrates the use of Qwen3-VL for vision language modeling. This model naturally is the latest and greatest from the Alibaba Qwen team, who are clearly pushing the envelope for VLM solution development. Before we start the death by PowerPoint slideshow, let us quickly look at how Qwen3-VL is a significant improvement over its predecessor. We will look at two basic areas: logic, reasoning, and coding. Let us do logic reasoning first. Observe the first picture. Which of the images in the second picture complete the pattern? Let's ask Qwen3-VL. In the first quick demonstration, we will feed Qwen with an image where one section is missing, and we will provide the answers in the second image and ask it to select the correct one. So let's go ahead and feed the images. We'll upload the files. That's the test image. And then the answer sheet we're selecting as the second image. And we're going to go ahead and ask Qwen the question, which is: observe the first picture, and which of the images in the second picture complete the pattern? So let's fire off this question to Qwen and let it go ahead and start processing. You'll see that it starts thinking, and very shortly it'll start doing its rationalization. Once the rationalization is done, then it'll go through the comparison of each cell by cell and come up with the answer. This is going to take a few minutes because I'm running this on a slightly older machine. So I'm without a GPU, and I'm going to go ahead and pause the video, and when the answer is presented, I'll have a surprise for you. So you can see that Qwen comes up with an answer which is C, and that's based on its rationalization. Unfortunately, C is not the correct answer. The correct answer is E. Please rationalize and explain. So I'm going to ask Qwen to go ahead and understand why it didn't perform the full analysis. So it's going to go ahead and start thinking and then come back and indeed confirm that E is the correct answer. So it's going to go ahead and figure it out. And once again, it's going to take a few minutes to do it. So I'll pause the video and come back when it's finished presenting the answer. So once I've given it the answer, Qwen is able to analyze and indeed confirm that option E is the correct answer. And it's given us the explanation also here. So this reinforces the fact that with most chat AI programs, LLMs or VLMs, you do have to converse with it so that iteratively, so that you can arrive at the best possible answer. Let us look at another example of logic reasoning by Qwen using a schematic diagram. In the uploaded schematic diagram, what is the minimum wattage required for the resistors in the schematic? Let's ask Qwen3-VL again. Let's give Qwen a schematic diagram. This is a PDF file, and I'll go ahead and upload it. And we're going to ask Qwen now to do some calculations based on the information in the PDF file. So the question is going to be, what is the minimum wattage required for the resistors in the schematic. And Qwen is going to start processing the PDF file and go ahead and display its calculations shortly. This is a pretty straightforward application of Ohm's law, but what I wanted to show you was that even if information is not present in the PDF file to help you to guide through the calculations, it knows enough about the fact that this is an electronic schematic and it can apply Ohm's law. So here it goes. It's basically recognizing that it's an Arduino board, so it knows the voltage for Arduino. It sees the text describing the resistance of each resistor, and then the application of Ohm's law will help it determine the current, and then from there we can get the wattage. So it's going to come up with pretty much standard sizes. You know, in industry, we don't have to we just round it off. And as you can see, it's rounding off the values and coming up with the answer that we're looking for, which is 1/8 watt. So here's the summary information based on the calculations and assumptions of the Arduino board and the LED power rating. And it tells us that it knows that it's a 5 volt, it knows the LEDs, and this is LaTeX information trying to represent on the screen. I wish I had a markdown sheet to show it for you, but that's the other side of it, that you can see that Qwen will generate LaTeX code. So it's 1/8 here. In our third example of logic reasoning, we will submit 3 pictures to Qwen3-VL. In this set of images, we will ask Qwen3-VL to select any picture or pictures that demonstrate high transparency but low reflection. In the third demonstration, let us go ahead and submit 3 images to Qwen. So I'll go ahead and upload the files. I have 1. The next one is 2. And then the third one is 3. And we'll go ahead and ask Qwen the question, select any picture or pictures from the uploaded set that demonstrate high transparency but low reflection. So let's see what Ken can do. And off it'll go, start thinking, and then it'll go ahead and start analyzing and come back with the answer that it demonstrates high transparency Qwen can generate code in C++, Java, Python, or many other languages. Here are some examples. Let us now turn our attention to coding. Let us ask Qwen3-VL to use the C++ language to create a graphical user interface to display civil dawn, sunrise, noon, sunset, and civil twilight times for a user-specified geographical location for a range of calendar dates. Use the detailed equations from NOAA, but do not use any external library for the ephemeris calculations. Allow the user to enter geographic coordinates and to select the date range. In the second demonstration of coding by Qwen3-VL, we ask for the generation of a Java program code to launch a ball from a moving robot to a stationary target. Finally, in the third demonstration of coding by Qwen3-VL, we will ask Qwen3-VL to illustrate the path of the ball in the preceding demonstration in 3 dimensions from different robot positions to the fixed target position. Use the Python matplotlib package to illustrate the paths in 3 dimensions. Qwen is a family of large-scale artificial intelligence models developed by the Alibaba Group. Qwen, short for Tong-Yi-Chin-Win, refers to the series of large language models, LLMs, while Qwen-VL is the multimodal variant that integrates vision capabilities. The Qwen-VL models are built upon the foundation of the Qwen LLM. This provides them with a strong linguistic core, enabling them to understand, reason, and generate human-like text. The vision language, or VL, part signifies that the models have been enhanced to process and understand visual information alongside text. Using a visual encoder, referred to as a vision transformer or whet in short, that converts images and videos into a format that the LLM can understand. Alibaba has released various versions of Qwen-VL to meet different computational needs. Many of these models are open-sourced, making them a significant resource for AI research in the development community. In this presentation, Qwen-VL represents the family of vision language models. The version release number is a model variant. Qwen-VL refers to the family of models. The specific model used for examples in this presentation is Qwen3-VL. There are 26 variations of Qwen3-VL models as generalist models. In other words, they are not limited to a single task, but can perform a wide range of vision language tasks. The highest accuracy and reasoning models are naturally proprietary, but there are plenty of open source versions for your self-study and learning purposes. The various Qwen3-VL models are differentiated primarily by their size, that is, number of parameters, and their intended function, which translates to differences in performance, speed, and hardware requirements. What are the high-level differences in the Qwen3-VL models? Well, Qwen3-VL models come in several versions, including dense and mixture of experts, MOE, architectures, and are also separated into Instruct and Thinking editions. The difference is size or parameters. Models range significantly in size from small variants like Qwen3-VL-2B for 2 billion and Qwen3-VL-8B to very large models such as Qwen3-VL-235B-A22B, a MOE model with 235 billion total parameters and 22 billion active parameters. The impact is that larger models generally offer superior accuracy and deeper reasoning abilities, while smaller models are faster and can run on less powerful hardware like consumer GPUs or even CPUs. The second difference is architecture. Dense versus mixture of experts or MOE. Dense models, for example, Qwen3-VL-8B or Qwen3-VL-32B, use all of their parameters for every task, offering more predictable latency and being simpler to deploy. MOE models, for example, Qwen3-VL-235-A22B, use only a fraction of their total parameters or experts for any given input, offering higher peak performance and greater efficiency, but often requiring specialized hardware setups. The third difference is function, that has two variations: Instruct versus Thinking. Instruct editions are aligned for general use, prioritizing speed and efficiency for most everyday tasks. Thinking editions are designed for complex problem solving. They employ an internal thinking mode to generate step-by-step reasoning called chain of thought before producing the final answer, making them better for complex math, science, and multi-step analysis. Naturally, we cannot perform a comprehensive comparison of everything in a single presentation. We will limit ourselves to the smaller models that can be run in CPU mode only. If you have access to the NVIDIA DGX Spark, then I wish you all the best sincerely. The fundamental trade-off for models is between power and accessibility. Model variants are about trade-offs. The Qwen3-VL models come in different sizes, from small, fast versions that run on standard computers to massive, more powerful versions that require cloud-level hardware to deliver the best possible accuracy. The common basic sizes of the Qwen3-VL models are 3 billion, 7 billion, and 72 billion. Users can balance performance with resource consumption by choosing specific models. Use case editions, you choose between Instruct models for general quick tasks like image captioning or Thinking models for complex work like solving a problem from a scientific diagram where the model needs to reason step by step. The Instruct model is your highly trained sprinter. It's built to follow instructions directly and give you the answer as fast as possible without pausing for deep multi-step analysis. The need for speed, latency. First, look at real-time chatbots. Whether it's customer support or a virtual assistant, users expect instant replies. The Instruct model is fine-tuned to have low latency. It doesn't waste time with a complex internal thought process. The key advantage here is simple. Speed and fluency are prioritized. If the user asks what color is the car in the image, they don't need a four-step derivation. They just need the answer, red. This is the Instruct model's sweet spot. Simplicity and directness. Next, consider how the model approaches general tasks. For simple image description, like general question and answer and rapid extraction, the Instruct model provides a direct, concise answer that meets user expectations. When you need to perform an action like, tell me all the text on this invoice, you care about the output format, not the model's internal steps. The Instruct model is optimized for quick, straightforward tasks where the final output format is the most important. An analogy is like asking a librarian for a book title. You want the title, not the librarian's entire history of how they filed it, deployment and cost, production endpoints. Finally, for engineering teams, the Instruct model offers a massive advantage for production endpoints. Because it's optimized to skip that verbose internal reasoning, it runs cheaper and faster at scale. In a production environment where you might handle millions of queries per day, this cost efficiency and high throughput is essential for keeping your deployment economical. So if your task is user-facing, high volume, requires immediate responses, or involves simple direct instruction following, the Qwen3-VL Instruct model is the right choice for efficiency and speed. This demonstration of a low latency, real-time customer support chatbot prioritizes speed and efficiency over maximum model size. The model processes both text prompt and an image through base 64 conversion in every conversation turn. You can take a photo of a product and ask questions in the same interaction. Since the script has a while loop control, it enables a fluid turn-by-turn chat experience required for live support with the full image context persisted for every query. Naturally, a CUDA-based is essential to achieve the low latency. Unfortunately, this demonstration is limited to CPU-only processing. By relying on the smaller 2 billion parameter Qwen3-VL model, the reduced computational load memory footprint, resulting in faster load times and quicker per-token generation. By using half-precision arithmetic, doubling memory efficiency, and significantly speeding up matrix multiplications, which are the core of LLM inference. Finally, by setting a low max new tokens, there are short, direct responses, which is critical for perceived low latency in a live chat where long wait times are unacceptable. Let us see the script in action now. Multimodal core capability, model selection. The script utilizes the Qwen3-VL-2B-instruct model, which is a visual language VL model capable of understanding and reasoning about both text and visual information simultaneously. Input processing. The design uses the standard messages array structure required by Qwen processor to seamlessly combine a text prompt, which is the question, with a downloaded image that's been encoded as a base 64 string for transport. This enables the visual question answering or VQA. Compatibility and portability focus. CPU-first rationale, the script explicitly sets the processing to CPU and uses torch.float32 data type. This design type choice sacrifices execution speed for maximum hardware compatibility and guarantees the script can run on machines without a dedicated GPU or high-end accelerators. Helper class, Qwen3-VL demo helper. The logic for model loading and inference is encapsulated, making the script clean and modular. The run underbar GQA underbar prompt method handles the complex steps of image encoding, prompt templating, and model generation, abstracting them away from the demonstration logic. Structured demonstration and testing. The demonstration suite includes a predefined list of 4 general question and answer tasks to showcase the model's different capabilities, including simple captioning, which is like describe the scene, detailed visual question and answer, what is the woman doing, reasoning, suggest a caption, object counting, how many dogs are visible, performance tracking. The script measures and reports the inference time for each GQA task, providing a basic benchmark of the model's speed on the current CPU hardware. Let us ask Qwen a basic question. What is the main subject of this image and what cuisine does it convey? Qwen3-VL, the 2 billion Instruct model responds, the main subject of this image is a dish of creamy white dip served in a brown bowl garnished with green pistachios and a small red cherry tomato. The dish is accompanied by a seasoned triangular tortilla chip, suggesting it is a type of appetizer or dip. The presence of the chip and the overall presentation are characteristic of Mediterranean cuisine, particularly dishes from the Middle East or North Africa. The dish is likely a variation of the traditional Middle Eastern or North African dip, such as hummus or similar creamy spread. If we post the same question to the 4 billion parameter model, we get a slightly more detailed answer in the form of 3 paragraphs and a short summary. So, in conclusion, you should always try to use the highest parameter model that is possible on the resources available to you. Here is the demonstration of a question and answer session using the Qwen3-VL model. Let us look at an example of a question and answer session using the simplest Qwen3-VL model that we have seen in this presentation. This Python script was adapted from the Qwen resources at HuggingFace. And on the left pane navbar, I have the structure of the script outlined for your quick review. As you can see, some of the functions that are already prepared in there. So let's scroll down now to the section where we are preparing the data for use by Qwen. So we prepare the payload for messages in this section of the code. The role is specified as user, and you can type in any string that you want that you feel would be appropriate for your role. And then we specify an image. Since this is a multimodal application, there will be at least one or more images, and then the prompt that you want. So let's go ahead and look at the prompts that we are going to be submitting to Qwen, and here are the basic prompts. The first question would be a very simple question to test the basic object recognition and a summary of the scene. So that's the first prompt that we're asking Qwen to analyze. And then we'll look at what are the colors that are dominant in this image. And we hope that Qwen will be able to sort the colors out and tell us what they are. And finally, we want some kind of an object counting. And so we'll ask Qwen to summarize the counts of items in the image. So let's see how the Qwen-VL 2 billion parameter model Instruct responds. So here is the response from Qwen with respect to our question and answer session. After loading the image that I have, it starts to process the first prompt, which is describe this picture in a single short sentence. And the response from Qwen is a seafood display at HEB market filled with various types of shrimp and other seafood, including wild Gulf shrimp, jumbo white shrimp, all on ice. And the ice is critical here, okay? So we ask the second question is what are the colors of the dominant items in the image? And based on the image provided, Qwen responds, the dominant colors are white, naturally because of all the ice and the packaging, and the shrimp themselves are mostly white and pink, right? And then it says blue is used for the large signs. I have a limit on the number of tokens, and that's why the response was cut off here. The next one was how many types of items are visible in the image, and then it identifies the types of image and the set of images that we have for the raw coastal Gulf shrimp, etc. Now, once again, I reduced the number of token count to 60, and that's why the response was truncated. Perhaps I should run it with a larger number of tokens and then get the more detailed response. I hope you've noted the previous response by Qwen. Let me show you what happens when I increase the number of tokens from 80 to 100 here. Okay, so once I do that and run the script again, I get more detailed information now from the system. So clearly, I have white, pink, and gray as the colors that are dominant in the image that was identified. Previously, I had only white there. And also, you can now see that it clearly identifies the different types of shrimp in there. Previously, I had only one. So it's important to have a balance between the number of tokens that you want as output versus the length of the conversation. So this is a very quick, short example, and I hope that you can try different examples on your own using the resources at HuggingFace.com. Architectural design for enterprise integration. Fast API framework. The script uses Fast API to create a modern, high-performance web API endpoint. This shifts the model from a local script to a network service, allowing multiple internal or external applications to query the GQA model concurrently. Structured I/O. Data models, image inference request, inference response, built with pedantic ensure strong input validation and predictable output formatting, including crucial metrics like latency. This is essential for reliable integration into production systems. Multimodal capability and data flow. Qwen3-VL core, the solution uses Qwen3-VL-2B-instruct model to support general question and answer GQA based on visual inputs. This is used for tasks like image description, visual document understanding, or answering questions about specific image features. Image handling. The API standardizes image transmission via base 64 encoding within the JSON payload. This is the common reliable method for sending image data over HTTP APIs, minimizing reliance on external file storage. CPU-first deployment strategy. Hardware agnosticism. The design explicitly forces model execution into the CPU. Device is equal to CPU and torch.float 32. This is a strategy for deployments where GPU resources are unavailable or too expensive. The primary constraint is memory, system RAM, rather than latency. Handling CPU latency. The synchronous blocking nature of the CPU inference call is managed using asyncio.io_thread. This is a critical feature. It moves the slow CPU-bound model generation to a separate thread, preventing the main fast API event loop from being blocked and allowing the server to handle other incoming API requests concurrently. Performance metrics and control. Response metrics. The inference response schema includes time underbar ms and tokens underbar second. This provides immediate per request metrics that are vital for monitoring API performance, especially in a production environment where latency budgeting is crucial. Generation control. The API allows the user to control generation parameters, including max new tokens and temperature, directly through the request payload, enabling fine-tuning of response length and creativity/determination on a per-query basis. If the instruct model is your quick sprinter, the thinking model is your deep diver. This version is specifically tuned for tasks where correctness and verifiable logic are more critical than immediate need. The thinking model takes its time because it generates an internal chain of thought, a deliberate multi-step plan before producing the final answer. In section 1, the domain of complexity is STEM and science. The primary domain for the thinking model is complexity, particularly in STEM and academic fields. If you feed it an image of a complex physics problem or a multivariable calculus equation, you want it to solve the problem, not just guess. For STEM or math reasoning, the key advantage is that it breaks down the problems step by step. This is crucial for educational tutoring systems or advanced analysis, ensuring the answer is logically sound and the methodology is visible. In scientific and data analysis, its strength lies in cross-referencing data. It can look at a complex chart, infer causal relationships, and analyze diagrams with a systematic approach that a simple instruction-following model cannot match. In section 2, trust and verifiability, diagnostic and agent tasks. The thinking model is also essential for high-stakes scenarios where trust and verifiability are paramount. In diagnostic and auditing tasks, such as analyzing a medical image or reviewing a legal document, multimodal context, the thinking model provides reasoning traces. This means you get a justification for the conclusion, adding crucial transparency and trustworthiness, which is non-negotiable requirement in these tasks. Even in automation like complex agent planning, the thinking model excels. It's not just clicking a button, it's planning a multi-step workflow on a GUI, verifying the outcome of each action and adjusting its plan accordingly. This leads to more robust and accurate task completion over long horizons. So in conclusion, the trade-off, to summarize the entire Qwen3-VL series, you must choose based on your priority. If you need speed, low cost, and a quick answer, use Instruct. If your task is high stakes, requires complex logical deduction, or needs a verifiable chain of evidence, the slight increase in latency for the thinking model is a necessary investment for the superior accuracy and reasoning depth. For the STEM math reasoning, we have a very simple example of multi-step reasoning. The user prompt is, calculate the total area of the figure shown in the diagram. The Qwen3-VL thinking process is the model executes a chain of thought reasoning sequence, perceives the key visual elements through visual parsing, identify the figure as a composite shape consisting of a square and right-angled triangle. The request to Qwen3-VL is calculate the total area of the figures shown in the diagram. Show your work. Qwen3-VL proceeds as follows. Loading model Qwen3-VL-2B-thinking to CPU. Model loaded successfully. Attempting to load image from composite area figure. Image loaded successfully. Starting CPU inference, expect long latency. This slide displays the complete response from Qwen3-VL thinking 2B model. The user prompt to Qwen3-VL was calculate the total area of the figure shown in the diagram. After executing a chain of thought reasoning sequence, Qwen3-VL responds with the text shown on the side. It identifies the figure as a composite shape consisting of a square and a right-angled triangle. It is able to calculate the area of each shape individually and sum the calculations for the total area. Owing to the limitations at my end, there is no CUDA and a small RAM and an ancient CPU, I had to use a very simple example. I sincerely hope that you have better resources at your disposal for more meaningful tests on STEM math reasoning by Qwen3-VL thinking model. Let's take a look at a simple script for STEM reasoning. I've adapted this for CPU inference only, and I'm using the code snippet prepared by Qwen3-VL team at HuggingFace. So the basic functions is to load an image and then to prepare the image and then run the reasoning. You can see the structure of the helper functions in here. The main part that you have to concern yourself with in these kinds of sessions is the fact that you need to be specifying the image and then what do you want to do with the image. In this case, I've said calculate the total area of the figures shown in the diagram. And there's not much else to be done except to keep an eye on the number of tokens that you want to specify. And you may have to iteratively adjust this. I've used 1024, and that means I want one big giant paragraph of an answer. Normally I use much less, about 512, to have a conversational session. So let's go ahead and run this and then see what Qwen3-VL produces. Let's review the results from Qwen. Obviously, it starts off by warning us that it's a CPU-only model and it's going to take a lot of resources. It's able to load the figure successfully, and then some transformers parameters should be ignored. And then since this is the instruct model that we're running, which is the Qwen3-VL 2B thinking model, it goes ahead and starts the rationalization and the reasoning response. And so it examines the composite figure. It understands that it is a composite figure, and it goes ahead and decomposes it into the basic polygon shapes and comes up with a triangle and a square. And then it goes ahead and finds out the area of the rectangle and the triangle, and then goes ahead and sums that up. It knows the formula for the triangle and the square, and it arrives at the calculation, which it says is 25 for the square and 5 for the triangle, and the total area is 30, which is indeed the correct answer. But essentially, in the simplest example, I just want to show you that it went through step by step. Its first step was to calculate the area of the rectangle. The second step was the area of the triangle. And of course, the third step is the summation for the composite figure area. The key highlights of the Qwen3-VL 2B thinking model, especially for multi-step reasoning, cross-referencing data, and systematic analysis of complex visual information, are reasoning optimization, the thinking variant. The model is a specific thinking model variant that is optimized for enhanced reasoning. Its core design focuses on generating detailed step-by-step logical reasoning. Systematic analysis for STEM. It is built to perform well on complex visual information, making it particularly useful for STEM and mathematical problems presented in an image. Its intended use, as demonstrated in the script, is to solve problems like calculating area from a diagram and explicitly showing the work. Systematic analysis, as we call it. Deterministic and logical output. The script configures the model with inference parameters that reinforce systematic analysis. Efficiency for enhanced capability. Even as the smallest reasoning model in its family, the 2B size still incorporates the necessary architecture to focus on this enhanced reasoning capability, making it a powerful, small-scale choice for tasks requiring structured logic over pure size-based knowledge retrieval. Let us use a simple stock price chart to demonstrate the advanced thinking features in Qwen3-VL. Once again, we have to limit ourselves to the smallest Qwen3-VL model, which is 2 billion parameters. The desktop where I'm running this model has no GPU, and its RAM is limited to 30 megabytes. Nevertheless, this demonstration is able to proceed to completion. The user prompt for this demonstration is: analyze the stock performance chart. Which company had the best 6-month return? And what can be inferred from the shape of the lines regarding investor sentiment? Let us see how Qwen3-VL responds. Here is the response from Qwen3-VL. Loading model Qwen3-VL-2B-thinking to CPU. Warning: requires several gigabytes of RAM. Model and processor loaded successfully. Attempting to load image from stockpricechart.png. Image loaded successfully. The following generation flags are not valid and may be ignored. Temperature, top P, top K. Set transformers verbosity equal to info for more details. Starting CPU inference. Expect very long latency. Requested problem: analyze the stock performance chart. Which company had the best 6-month return, and what can be inferred from the shape of the lines regarding investor sentiment? And here comes the response from Qwen3-VL. Here is the reasoning response. Got it. Let's tackle this problem step by step. First, I need to figure out which company had the best 5-month return. The chart shows normalized stock price movement, where the x-axis is normalized percentage minus base equal to 100%. So the higher the value, the better the return. Since it's normalized, the percentage change from the base is the return. Looking at the three lines, INTC, which is blue, NVDA, which is orange, and Sony, which is green. Let's check the peaks and troughs. The blue line, which is for Intel, has a peak around 2025-11, reaching close to 180, which is way above the others. The orange line, NVIDIA, also has a peak, but may not be as high. The green line, Sony, is more stable and maybe around 120 to 130, but not as high as Intel. Wait, let's check the values. The y-axis goes up to 180, so Intel's peak is the highest. Let's confirm. Intel's line goes up to 180. NVIDIA's peak is maybe around 160 to 170. Sony is lower. So Intel had the highest normalized price, meaning the best return. Now the second part, what can be inferred from the shape of the lines regarding investor sentiment? Let us look at the trends. The blue line, Intel, has a lot of volatility, fluctuations, spikes, and dips. The orange line, NVIDIA, also has volatility, but maybe less than Intel. Wait, NVIDIA's line has some peaks and valleys, but Intel's line is more erratic. The green line, Sony, is more stable with less fluctuation. Investor sentiment is often reflected in how much the stock moves. If a stock has a lot of volatility, high fluctuations, that might indicate high sentiment, either bullish or bearish. But in this case, Intel had a very high peak and then a sharp drop, but then a recovery. Wait, the shape. Intel's line has a lot of ups and downs, which could mean that the investors are very optimistic, high sentiment. When the stock went up, then maybe pessimistic, low sentiment when it dropped. But overall trend for Intel is upward with a lot of volatility. Wait, let's think about it. So you can see I printed the output from Qwen on the slide here, and I just read it out for you. So I hope you get a feel for how the thinking model works. The Qwen3-VL 2B thinking model, despite its small 2 billion parameter size, offers specific architectural and training enhancements that make it highly capable for complex agent planning in a multimodal vision language context. The key insights in its solution for complex agent planning are rooted in its thinking modality and its ability to process complex visual and spatial data systematically. The three areas are thinking core, where internal reasoning traces are generated in a structured manner; action planning, where the model is explicitly designed to handle tasks requiring an agent to act on a visual interface as part of the complex planning; And finally, situational awareness with superior spatial and temporal ground. Let us drill down into each of these areas at a high level. Structured internal reasoning, the core of thinking. The thinking variant is explicitly trained to generate internal reasoning traces, often exposed as think block in larger models of structured reasoning in the output. This feature is crucial for complex agent planning because it enables multi-step planning. The model breaks down a high-level task into necessary sub-steps before acting. For an agent, this translates to goal, step 1, which is visual perception, step 2, tool and action selection, and then step 3, which is execution and refinement. Compositional skills, it can combine different pieces of information on different skills, visual, textual, tool use, in a logical sequence to achieve a final goal, which is the definition of complex agent planning. Every single action an intelligent agent takes starts with looking. This is the first step, visual perception, where the Qwen3-VL model uses its vision capabilities to simply see the problem. Let us look at the action. The first action is to invoke a multimodal OCR grounding tool. This isn't just taking a picture, it's like giving the AI a pair of smart glasses. We use two main technologies here. Optical character recognition, this is the basic step. It reads the text like the titles, axes, and the legends on the chart. Grounding, this is the smart part. The model doesn't just read the text, it understands where that text is and what it relates to. It links the word sales to the height of a specific bar in the chart. The target is simple. Scan the complex bar chart image. The model systematically goes over the entire image to collect every piece of information. It's looking for the main title. It's looking for the x-axis labels like product names or dates. It's looking for the y-axis numbers, the sales figures. The key takeaway here is the output. The model doesn't output an answer yet. It outputs structured data. It extracts the text labels, product A, Q4 sales. It extracts the raw chart values, the actual numbers. And crucially, it generates coordinate bounding boxes, which means it knows exactly where everything is located. This structured data is like turning the messy visual image into a clean digital spreadsheet. This sheet is what Qwen3-VL thinking part of the model will use in the next step to perform its logical reasoning. In summary, step 1 is all about converting sight into clean, structured data, the foundation for intelligent decision making. Let us perform a very simple demonstration to illustrate the Qwen3-VL thinking model. Our goal is to open the settings menu and change the user avatar using icons visible on the mobile screenshot. Naturally, our input will be a screenshot of the mobile app. We will step through the process. The first step is observation, the second step is analysis, and the third step is execution. Once the planning is complete, we will be ready for tool execution. Let us run the program, and then we will examine the output from Qwen3-VL thinking model in a stepwise manner. The Qwen3-VL thinking model generates structured output. Qwen3-VL 2B thinking model is special because it is designed to output the structured step-by-step thinking process, like step 1, step 2, step 3 format in the script, before it gives the final answer. In the initial phase, which is the planning phase, the agent is deciding how to solve the problem, not just solve it. If step 1 was about seeing the data, step 2 is about thinking about the data. The goal here is simple. Use the clean, structured data that we extracted in the first step to answer the user's complex question. This is where Qwen3-VL thinking model does its heavy lifting. The action is to process the extracted data using the internal reasoning trace. Think of reasoning trace as the AI writing out its thoughts, like showing its math homework. Instead of just giving the answer, it tells us, I will look at the numbers and then I will compare them, and finally I'll select the largest one. This step-by-step logic is what makes Qwen thinking model so powerful. It makes the AI's decision transparent and verifiable, just like a human analyst's report. Let us look at the specific sub-steps for the analysis goal. Cross-reference. Identify the maximum. This is the comparative task with a quick sorting operation. Determine the product name. Trace the maximum value to its source. The output of this second step is a verified intermediate conclusion. The agent has seen the data and solved the problem. The final step is packaging that solution neatly for the user. We've reached the final step, which is crucial for delivering value. Execution is the phase where the agent takes the confirmed answer from the thinking process and prepares it for the user. It's the moment the computer's work becomes a human-readable result. The action is to format the final verified result. In the previous step, Qwen3-VL thinking model determined the answer. Product B is the top seller, but that answer is still raw data within the agent's memory. This step forces the agent to interact with the outside world. It ensures the answer is not just logically correct, but also structurally correct for the target recipient. If the goal required a JSON file for a database, this is the step that creates the JSON file. If it requires a simple sentence, it builds the sentence. The chosen format here is return product results in a human-readable manner. This is an important step because it ensures usability. A good agent shouldn't just dump data, it should deliver a polished communication. For our bar chart example, this step transforms the raw data points into a clear, complete statement like, based on your Q4 sales chart, the top selling item is product B. This demonstrates the agent's ability to synthesize its findings. In summary, the entire three-step process, perception, reasoning, and execution, shows how the Qwen3-VL thinking model, even at a small 2B size, is designed for complex agent planning. It sees the image, step 1. It thinks about the data and solves the logic problem, step 2. It acts by formatting and delivering the final result, step 3. This structured, reliable approach is what makes the thinking variant a powerful foundation for real-world AI applications. The Qwen3-VL thinking model is explicitly designed to handle tasks requiring an agent to act on a visual interface, which is a major component of complex planning. Graphical user element recognition. It can perceive GUI elements, understand their functions, and can plan steps to complete tasks across desktop or mobile interfaces. For a small model, this capability is a breakthrough, enabling it to map a user's goal, for example, book a flight, onto a multi-step sequence of visual actions, click, scroll, type. Visual coding boost, the ability to convert design mockups into code using draw.io, HTML, CSS, or JavaScript demonstrates a deep structural and relational understanding of visual layouts. This is a foundational skill for an agent that needs to analyze a screen and understand not just what elements are there, but how they relate to each other structurally. For example, a button belongs to a form. This demonstration uses minimal resources to provide a basic example of thinking models using Qwen3-VL thinking. Naturally, there is a fine balance between comprehensive capabilities and resource requirements. Spatial reasoning and viewpoint change in turn 2. The model must maintain an absolute position for the red box and blue cylinder from turn 1. It then processes the relative command, moved 2 steps left, and recalculates the relative position based on the new viewpoint, simulating sophisticated spatial logic. Long context multimodality in turn 3. The model must ignore the intermediate information from turn 2. Forget the last move. It retrieves a crucial detail, object next to the red box, that was only available and stored during the initial observation in turn 1, the green sphere. It then generates a systematic execution plan. Go back, navigate, pick up. The printed internal reasoning trace is the central element, proving that the model is performing multi-step reasoning and cross-referencing historical data, which is the definition of situational awareness in a complex agent. One final demonstration, please. The focus here is on the core concept of multimodal reasoning and constraint fusion performed by Qwen3-VL thinking agent to demonstrate a multi-step logical plan. In step 1, the perception step, the agent analyzes the image and extracts base attributes. The model uses visual grounding to establish the core product features. In step 2, the reasoning phase, the agent analyzes the user's text and performs constraint integration. The thinking mechanism fuses conflicting data to determine the correct intent and priority. In step 3, the action step, the agent generates a precise, structured query containing the fused and final attributes. The detailed thinking trace enables the generation of a highly accurate executable query for an external tool. And then we arrive at the final agent response. I have successfully fused your visual input and text constraints. I am now searching for a dark forest green, chunky cable knit sweater with a maximum price of $59.99. Let us conclude this presentation with a nominal comparison of the Instruct and Thinking models. We will use the same chart as shown here with both models. We will also use the same script, but simply change the name of the model when we run the script. Here is the common script. The first run is with the Instruct model. The payload will remain the same for both runs. Let us scroll down to the key sections of the code where we're going to change the information. So first of all, we're identifying the model as the Instruct version of the VL2B. We're going to be using CPU only for demonstration purposes, and the chart is identified here. So if we go down further in the script, and you've all seen this before, it's derived from HuggingFace. We have the payload defined here. It's a single image, and we also have the chart prompt that I'll show you shortly. And then there are some standard processor information, and I've set the token for now just to 512 for experimental purposes. If we do need to change that, we can go ahead and do it later. So when we run the Instruct model, the question is going to be analyze the bar chart. And this is the same question that we'll pose to the thinking and compare the answers. So let's go ahead and run this with the Instruct model. Here is the output from the Instruct model. As you can see, it did a very good job of looking at the chart, reading the revenue numbers, and then going ahead and summarizing the information and performing a basic analysis. The key thing to note here is that it was a single shot. It just ran the analysis and reported it in one paragraph, which is what the Instruct model is supposed to do. So let's go ahead now and use the thinking model and see what we get. So the only change that I'm going to make is in the type of the model, and this will be thinking. So just let me go ahead and type thinking in there. And everything else remains the same. It's still a CPU solution. The file, of course, is going to be the same because we're doing a comparison. And notice that the payload remains the same, as does the question that we're going to be posting, which is exactly identical. And we'll see how the thinking model responds. Let us look at the output of the thinking model. It's the same file again, bar chart. and it starts off and confirms that everything is okay as far as the input is concerned. And notice now that it creates a basic stepwise reasoning for what is going to come up as the answer. So we have step 1, step 2, and step 3. The answers, by the way, are identical to what the Instruct model created, but here there is reasoning provided behind the calculation. That's the key distinction between the Instruct and the thinking model. So if you want quick answers in like a chatbot style, go for the Instruct model. If you want long logical reasoning provided to you by what the model did, then go ahead and use the thinking model. I hope this gives you a very, very quick insight into which model to choose. And of course, I've used the lowest resources possible, which is the 2 billion parameter model. This tutorial demonstrated a popular vision language model. Qwen3-VL is free open source software for your education and research journey into the exciting world of multimodal solutions in artificial intelligence. The top versions of the models in this family are proprietary. This presentation listed some of the key benefits and features of Qwen3-VL using the 2B versions of Instruct and Thinking models without having the luxury of a CUDA device. While it is impractical to run VLM with limited resources, such as no CUDA support and low RAM capacity, one can run the 2B models in this manner for self-study purposes. Since it is very easy to swap out models once you have a grip on your simpler model, you can seek more resources to run larger models. Naturally, you will enjoy more accuracy with the higher parameter models. So treat the exercises in this tutorial as a basis for getting started and ensure that your code is operational. Then migrate to cloud-based resources, if possible, to enjoy the benefits of larger models. That's all, folks. Thanks for taking the time to view this very long presentation. I trust that you understand that it is really important to explore visual language models using a platform that matches your interests. Would love to hear from you with your feedback. You're always welcome to be critical in any which way you can. Until next time, bye for now. The Qwen3-VL diagram on this slide is from the documentation by the Qwen team at HuggingFace. Its use here is purely to provide a reference for your use should you need it. This presentation was prepared with assistance using free open source software, FOSS, from the Qwen team at Alibaba. And for the backbone of the preparation of this tutorial, from OBS Studio, Kdenlive, LibreOffice, JetBrains, and of course Ubuntu. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.